Hello, this section is on section 7.1, which is titled Exploring Exponential Models, and the learning target is to model exponential growth and decay. So there's two different types of exponential models. First one is growth, and the second one is decay, and we'll get into more detail on that in this video. But first, before we get started off, the general form for an exponential function is y equals a times b raised to the x power, and your only criteria on what a and b can be is that your a is not equal to 0 and your b is positive but cannot be equal to 1. If it's equal to 1, it's going to be a straight function, not going to increase or decrease exponentially, and it must be positive. So taking a look at how we can graph some of these exponential functions, if we have y equals 2 raised to the x power, take a few x values, -2, 1, 0, 1, 2, and just replace them with the x in your equation. So 2 raised to the -2 power becomes a decimal 0.25 or 1/4. Then 2 raised to the -1 is 0.5 or 1/2. And 2 raised to the 0, and since anything raised to the 0 is 1, 2 raised to the 0 then becomes 1. 2 raised to the 1 is 2, and 2 squared is equal to 4. Plotting each of these points on a graph and connecting the dots into a line or a curve, then that is what the equation is going to look like. Now you can use your graphing calculator sometimes, as long as you use the caret button and then the x, or if you're not able to use a graphing calculator, pick a few points, find an x and y coordinates, and draw some points and connect the lines. Okay, now the difference between a growth and a decay is that if you have a growth, then it is going to be an increasing function. And in order for it to be increasing, that means that your b is less than 1. And in order for it to be a decay, or greater than 1, sorry, not less than 1, your b must be greater than 1. Now in order for it to be a decay, that is a decrease in an exponential function. And this means that our b is between 0 and 1. Since our b must always be positive, we can't just say b is less than 1. We have to say that b is also greater than 0. So it could be a fraction 1/2, 1/3, 1/4, 3/5, whatever. As long as it's between 0 and 1, then it is a decay of a function. So since this kind of determines whether our function is a growth or decay, that means that our b is known as our growth or decay factor. Just kind of depending on which type of equation we're looking at, that is what our b is known as. So taking a look at a few examples, if we have y is equal to 12 times 0.95 raised to the x, a way you can determine whether this is a growth or decay is you know that your b is equal to 0.95. So since it's between 0 and 1, this is a decay. And in other instances, you may be asked to find what the y-intercept of this equation is. And in order to do that, you just replace your x with 0. Anything raised to the 0 power is going to be 1. And 12 times 1 is 1. So this is known as the y-intercept. Just replacing our x with 0. I think we touched a little bit on it in AG 1 and 2, which is a refresher. Y-intercept, plug in 0 for x, solve for y. One more example, we have y is equal to 0.25 times 2 raised to the x. We know that our b is equal to 2. Since it is greater than 1, this is an exponential growth. Then finding the y-intercept of this equation, replace your x with 0. Anything raised to the 0 power is going to be 1. And 0.25 times 1 is 0.25. So in both of these examples, it's just the number that's out in front, but a lot of times if you have a horizontal or vertical shift, it may not always be just that number. So the easiest way or the most effective is to just replace your 0 with x and then solve, because you may have to do some other stuff like adding at the end, subtracting, dividing. It just kind of depends on what your equation is. But both of these examples were nice and easy, where those are the numbers that we have. Now actually looking at how we can model some of these, the one equation I want you to use and over again and memorize is a of t equals a plus a times 1 plus r raised to the t power. And each of those letters have meanings. They represent something. Our a of t is equal to the final amount, just kind of depending on whether it's increasing or decreasing at the very end result. That's what the final amount is going to be. The little a is the initial amount, whatever we started out with. The r is our growth or decay factor, or the rate, and t is the time, the amount of time it's being exponentially growing or exponentially decaying. And so if we have an example that's looking into kind of investment and a savings account, let's say you invested $1,000 into a savings account, and it's going to give you 5% interest every year on the money that you have in the account. So if we want to figure out how much money will be in there after 6 years, we look at our modeling equation, a times 1 plus r raised to the t, and each of the letters we need to find what they represent. This is our initial amount, or our a. The 5% is our rate, and our 6 is our time. So since each of those letters are right here, r is 5% and t is 6. Now your t is always going to be in years, and since it's already in years, we don't have to change anything with it. But if sometimes you're given months, you'll have to convert this to years, or if you're given days, you'll have to convert it to years. Just always convert your t to years. And then our rate must always be written as a number. So instead of 5%, you move the decimal over 2 spots to get your new r of 0.05. And that is the number you plug into the formula. Don't ever plug in it as a percent. So plugging in all the numbers that we have, 6 for t, 1,000 for a, and 0.05 for r. 1 plus 0.05 is, of course, 1.05. And if you plug all this into the calculator, you will get a number that is approximately $1,340.10. I am rounding up to the nearest hundredth, since that is all money is it's to the second decimal place. And since we started out with $1,000 and we ended up with $1,300, that means this is an exponential growth. And we ended up with more money than we started out with. That's usually how savings accounts work. Okay, thank you.